Well, we will see similar things, of course, as you can imagine. In practice. So that's you see a lot of orders here, and that's because many things I will present is from a large study about drought in the central area of the Netherlands, executed by these institutes, and I will show you results from that. Well, as Marijke already told, the impact was on agriculture, on shipping, on nature, especially of course, well, streams fell dry, but also moorland pools and peat bogs were really deteriorated by the drought. And of course, streams run dry and groundwater levels were extremely low. And that's the topic I'm going to focus on. If we look at the Netherlands, we have, well, you can divide it in three main regions, which is the purple one, it's the peat area, the green blue one is the clay area, and the center area is yellow. And also for the center area, there's not much water supply possible. If we go to the coastal area, where we find the saline groundwater very shallow, which is flowing upward in our deep polders, it salinized our surface water systems. And you can imagine what happened during the drought, that there was less precipitation, so less dilution, and salinities increased. Also, we had enhanced seawater intrusion because the rivers have lower discharges. And there are some main intakes of river water, and they also salinize. So it was a real deficit of fresh water in this area because of this salinization. Now we go to the sandy area, and the remainder of the presentation will go about this sand area. It's a large part of the Netherlands. And the results I show you, we use a model to calculate effects of this drought, and we did with our national hydrological instrument. I will not go into detail, but mud flow is used for the groundwater part, the unsaturated zone with metaswap, the actions of course, and for the regional surface water system is Mozart, and there's also a national distribution water system. And well, all parts of the water system are modeled with this model, so it's really suitable to calculate effects of droughts and also solutions. So if you look to a typical sand area situation, we have of course higher areas where water is infiltrating towards the brook valleys. And a drought starts of course with the weather. It's less precipitation, more evapotranspiration, and then it propagates to the soil moisture. So that's the first plants get it more difficult to transpirate, that's what the plants do, and then it propagates to the groundwater system. And it depends on where you are in the groundwater system, if there is a delay or not. In the higher areas, you have deeper groundwater levels, and there will be a larger delay than in the wetter areas. And then finally, as Marijke already said, is that most of the groundwater ends up in the streams, in ditches. So when the groundwater levels are lower, you will also find lower stream flow. So these aspects, I will show you some calculations. First, you see here the actual transpiration by crops divided by the potential transpiration, so what they optimal can do. And when this factor is close to 1, they have an optimal transpiration. That's good. And that happened in most areas here in 2017, which is a normal year. But 2018, you see more red colors, which this factor goes below 50%, and that's really because that many crops and also nature has had problems, had damage. Also 2019, you see it was a little bit less extreme than 2018. Now, if you go to the groundwater system, also calculations, you see here the difference between 2018 and the average of 30 years. In April, you see a lot of gray, and nothing is happening yet. But in the summer, in the entire area, we find groundwater levels which are 20 centimeters up to 1 meter, 1.5 meter lower than on average. And it's still, it was in October and also November and December. The same we saw in the time series. KWR within our project did the time series analysis. They calculated the standardized groundwater index, and when it's lower than 1.5, we talk about the groundwater drought, which is extreme. So also in April, nothing is happening. In June already some orange colors are appearing, and in July everything, almost the entire area is dark red. Then to the end of the water system, the catchment discharge. This is summed catchment discharge of the water board of Brussel Delta. See here for the entire years the regime curve. So this 90 percentile of 30 years of discharge, and this line is 2018. And you see that in June it was still okay, but then in July it really drops below this curve, and it stayed there for a long time. Only in December, January it recovers. This is for the entire center. Very important issue is the extractions from groundwater for irrigations. Farmers extract water for irrigation of crops, which is really good for the crops, but it's had negative effects for the water system. They extracted about 2.5 times more than average. You can see here, I think it's about 150 million cube they extracted in 2018. Here you see the registered one. And it has a really strong impact because they do it on the driest period of the year. I will show you some effects, some explanation, because a lot of people say, well, we extract deep groundwater, so it has no effect on the shallow system, but that's not true. They extract here, you get an aquifer head decline. It has a direct effect on your phreatic groundwater level, which has its effect on the stream flow, and also because of this lower aquifer heads, there is much less upward groundwater flow in the brook valleys. And this you can see in these monitoring results. They are already 20 years old, older, yes, but they nicely show what's happening. So all the groundwater abstractions are in the aquifers, below some clay layers. And here you see the aquifer head, which normally should do this dashed line. But the yellow part, that's the effect of these abstractions. You see, in this case, more than 1 meter, it drops, and when they stop with irrigating, then it recovers. It takes some weeks. But also the groundwater level, we measured here in the Brook Valley, very close to this hydraulic head measurement, also shows these drops. You see here, also here, especially here. And so it's shown really nicely that it is affected. And also the groundwater seepage in this Brook Valley, because we have higher heads in this case. Groundwater is flowing from higher heads to lower heads, and this difference, that's the driving force. And well, it's okay here, but you can see it reduces to zero in these kind of periods. We calculated this also with the groundwater model, the national instrument, and here you see the effect of these abstractions in 2018 on the summer aquifer head. You see higher effects, larger effects in this area. It's not because they extract more, but it's because the clay layer is more developed. It's semi-confined hydrogeologist here. And if you look at the phreatic groundwater level, you see here that the entire area is affected from effects of about 25 to half a meter, 5 centimeters to half a meter in some areas. And importantly, the effects are still visible in 2019. So when we start the growing season on April, this is what is left of the abstractions in the summer. The abstractions, as I explained, also have its influence on stream flow. It's maybe a difficult graph, but what it's saying is that it's the effect of different catchments, the effect on discharge. This is the irrigation period, and the effects are the largest, absolute, in the winter. Because then this whole discharge process is going to happen again. But more important is that during the summer, and this graph here, we see the relative effect, that at the end of the irrigation period, 25% of the discharge is affected, because we have very low stream flow, but these abstractions has this effect. So it's already low, and it reduces it by 25%. Well, we did a lot of calculations, and this is already known for a couple of years, but a strongly affected groundwater system is much more vulnerable to droughts. And there are two main causes, and that's the intensive drainage system for agriculture, a lot of ditches, especially after World War II. They drain the water very quickly to the sea. And also the increase of the use of groundwater for drinking water, increase since the 1950s. So this is my last slide. So if you want to make the water system more climate robust, well, you saw on which parameters you should focus on, and that is the redesign of the water system, and not for drain it too quickly to the sea, but keep it groundwater levels higher. I think also restrictions of groundwater abstractions, both for drinking water and farmers. Of course, we should drink, but there are alternative sources, for example. And we can have some technical solutions, increase the groundwater recharge, for example, manage aquifer recharge, extra infiltration of water. It's a lot of topics here in a lot of presentations at this conference in Denmark. And that's a good way to compensate, for example, drinking water systems, or to recharge groundwater systems. And well, these droughts will occur much more frequently, and it's good to have more monitoring data and actual data, and also models to predict how the system is responsive. And that will be in the next presentations talk about this. So that was my presentation.